Okay, good evening everyone, and you're welcome to another South Dublin Radio Club Tuesday night lecture. Before I introduce David and Fergal from EIRSAT-1, I'd just like to say a few things. If this is your first time with us, you're most welcome, and if you're a return guest, thanks for your ongoing support. The aim of these Tuesday night talks is to educate and inform, and also to promote amateur radio as a great hobby and a gateway to learn about and have fun with science and technology. But the presentations are not exclusively aimed at the amateur radio community, they're for everyone, and they're open to the public. So if you're not an amateur radio person or involved in that end of things, you're very welcome to our club's public talk tonight. All presentations are recorded, and you can find our previous talks on our YouTube channel. And indeed, you can keep up to date with our activities via social media, on Twitter, Facebook, on YouTube, and on our South Dublin Radio Club website. And we've put links to those in the chat, so please visit us there if you want to keep tabs on what we do. If you're a keen listener to shortwave, etc., we also advertise upcoming talks via the Irish Radio Transmitter Society. That's our national body, through their HF and VHF news service. So you'll also get details there on their Sunday bulletins and bulletins throughout the week. Regarding the running order of tonight's talk, the audience will be muted for the duration of the presentation. And for the questions and answer session, and to avoid audience members talking over to each other, we'll be taking questions via the chat function. Where if you have a question, just put your name in the chat and we'll call on you then to put a question. And my colleague Derek will put questions from you to David and Fergal. So he'll go to you and ask you to put your question. So he'll moderate that end of things. And then just a reminder, we have a presentation next week. That presentation will be given by Joe Ryan, EI7GY. And it's a talk on the radio experiments by Colonel Dennis, and his call sign was EI2B. And Joe's presentation will cover the experiments conducted by Colonel Dennis from 1898 to the 1930s. And this gentleman is widely considered the world's first radio amateur, so that should be quite interesting. Anyway, on to tonight's lecture and introduction. So it's with great pleasure that I introduce David Murphy and Fergal Marshall of the EIRSAT-1 team. So this will be Ireland's first satellite, so it's very exciting. David is a postdoc in the UCD Space Science Group. He graduated with a BSc in physics with astronomy and space science from UCD, and went on then to complete an MSc by research in UCD. David has worked extensively on CubeSats during his master's and PhD, including EduCube and the development of the GMOD, that's EIRSAT-1's gamma ray module, which was the main topic of his PhD thesis. He has taken on the role of systems engineer for EIRSAT-1, overseeing the design, testing, and integration of the spacecraft and its subsystems. Fergal is an MSc student in the School of Computer Science at UCD, and he graduated in 2018 with a BSc in Physics and Astronomy and Space Science from UCD. In 2019, he graduated with an MSc in Space Science and Technology. And he began working on EIRSAT-1 through a 3-month internship as part of the Space Science and Technology Masters. And he's continued his work in his current masters, and his work is focused on the EIRSAT-1 ground segment communication software. So guys, you're very welcome to South Dublin Radio Club Tuesday night lecture series, and we're very grateful for your time. So I'll hand it over to, I think David's going to speak first, and we're very much look forward to what you have to say to tonight.
Great, thanks. Let me just share my screen here. Okay. Okay, does that look okay to everyone?
Good.
Okay, great, thanks. First of all, thanks for reaching out and inviting us. A really good opportunity to interact with the amateur community. As you said, I came from a physics background and astronomy and space science, and my PhD has been focused on gamma ray detectors and stuff. So when we got this opportunity to launch or to design EIRSAT-1 and to build it up, we had to put together all these sort of skill sets, and one of those things was, the comms, and it hasn't been the easiest path to get to where we are. And we always knew that we wanted to engage with the amateur community, and we've had some fantastic help from the amateur community already, from Seamus McCaig and Dan Cusson and Rory Hinchy, amongst others. But I think we're just about reaching the point where we're sort of confident to sort of properly interact with the amateur community, and we're kind of on your level now, mate. Well, probably not on your level, but getting to the point where we can kind of understand it all. So I think we're at the level where we can hopefully start interacting and hopefully build up a good relationship between the EIRSAT-1 project and the amateur community. So first of all, what is EIRSAT-1? So as Adrian mentioned, it's set to be Ireland's first satellite. It's a 2U CubeSat being developed by a student-led team at UCD. And back in May 2017, we were one of 6 university teams that were selected to participate in ESA's Flyer Satellite Program. So that's run by ESA Education. It's run by the ESA Academy, which is sort of the subset of ESA that deals with third-level students. And the Flyer Satellite Program supports student teams to develop, build, test, and launch a CubeSat. And it does that by providing access to state-of-the-art test facilities, really just like absolute top-level test facilities that have been designed just to support us. It's really incredible what they're doing for us. And we get guidance from experts from ESA. If there's any sort of question that we have where we're not sure about anything, we have access to all of the ESA experts, which is incredible. And if we hit certain milestones, which luckily we have been hitting those milestones so far, ESA will provide a launch opportunity. So they will take our satellite into space and deploy it in orbit for us. And the mission aims of EIRSAT are to, firstly, enhance the capabilities of the Irish education sector in space science and engineering. It's something that there's not a lot of experience in Irish institutions. Broadly speaking, I mean, there are some very talented people that do a lot of good work, but in terms of having programs that can pump out students that are really talented in space science, that doesn't really exist. So we're trying to foster that, and we're going to perform the first in-flight test of 3 experiments that were developed at UCD. So this is the EIRSAT team, notably without myself or Fergal. So this picture was taken on a day that both myself and Fergal were out sick, but this is the rest of the team, and you can see myself and Fergal in the little chat windows. But you might be wondering, what is a CubeSat? So a CubeSat is a particular class of nanosatellites that conform to a standard called the CubeSat standard that was developed by California Polytechnic. It's made up of multiples of the standard 1U CubeSat, and you can see a 1U CubeSat drawing here from the CubeSat design specification. And it's basically a 10 centimeter by 10 centimeter by 10 centimeter cube. So that sort of yellow volume there that you see in the drawing is a 10 centimeter cube. And then there are certain protrusions that make it in actual fact a little bit bigger, and there are lots of little details to contend with. But basically 1U is a liter of space, 10 by 10 by 10 centimeters. And going by the original specification, 1U should be less than 1.33 kilos. Some rockets that have CubeSat deployers will allow you a little bit more these days, but the classical spec is 10 by 10 by 10 and less than 1.33 kilos. But you can put CubeSats together. You can basically say, I want to have multiples of this volume and this mass. So typical configurations are 1U, 2U, 3U, where they basically just stack them all up together along in a tube, and then you get to 6U, where they start getting wider, 8U and 12U. And they're dispensed from a larger spacecraft using a rail system, and you can see those rails in the drawings here, the gray rails on the top drawing, and you can see it as well on the EduCube has these rails here, and this is how the CubeSats are dispensed from the larger spacecraft, and that looks a little something like this. So this is 2 3U CubeSats getting dispensed from the biggest spacecraft, the International Space Station. Just to see that again, they're basically loaded into a box with a spring, and there's a door that prevents them from getting out. And then when the time comes, that door opens and the spring just pushes them out. And that's it. They are now free floating in space. They're in orbit by themselves. They have no support from any bigger spacecraft. They have to power themselves. They have to provide comms. They have to do absolutely everything that a bigger spacecraft does, except in a 10 by 10 by 10 volume. So as you can imagine, that's quite challenging. It's not easy to shrink everything down. And there's definitely been meetings I've been in where I'm arguing with someone else over what 1 millimeter slice of the spacecraft belongs to them, and so on. So it's a lot of stuff to fit into what in EIRSAT-1 is a 2U CubeSat, so essentially 2 liters of volume. So this is what EIRSAT-1 looks like if you open it up and take the side off, and you can see that it's basically a stack of subsystems. So it's basically a stack of PCBs that all connect together. Each one has a different function, but they all connect through a common bus and talk to each other and share power. So our 3 payloads that we have are 3 experiments. The first is GMOD. It's a gamma ray detector based on a design that was developed at UCD under contract to ESA. And that's designed to detect gamma ray bursts, which are formed or occur rather when very massive stars explode at the end of their life, or you sometimes see them when 2 compact objects, like a neutron star, 2 neutron stars in spiral and eventually merge. It can produce lots of gamma rays, and it also produces gravitational waves, which have been a very hot topic in the scientific community lately. The second experiment is EMOD, and this is going to make measurements of EnBIOS solar black and solar white coatings that they develop for Solar Orbiter. You can see these are on the top of the spacecraft. The black and the white sort of Battenberg pattern is EMOD. And then finally, we have wave-based control, which is a control scheme for flexible mechanical systems. It was developed at UCD. So how that's going to work is that's going to control the attitude of EIRSAT-1. So the attitude is just the direction that it points in space. So that's going to use the standard off-the-shelf attitude hardware, but UCD is providing a software algorithm that's going to control it and hopefully demonstrate an algorithm that works better than the standard algorithm that you purchase that comes with the attitude control system. So looking at the stack from top to bottom, as I said, we've got the EMOD thermal coupon assembly. Underneath that, you've got the actual GMOD gamma ray detector itself. Then further down, we've got the EMOD motherboard, then the attitude determination control system motherboard, the onboard computer, the EPS, which is our electrical power system. So that takes in power from the solar cells, charges the batteries, then takes power from the batteries, regulates it to the various voltages. It has a bunch of protection circuitry. We can turn on and off various subsystems by cutting their power. And yeah, it's basically, it's the one thing that just has to work rock solid for your satellite. Below that, we have the battery, then we have the comms board, and then we have the Z-axis magnetorquer. And then finally, on the very, very bottom, we have the antenna deployment module. So I'll talk a tiny bit about the antenna deployment module, but I believe Lana has been in touch to, at some point in the future, arrange a talk all about the antenna deployment module, because it's a really interesting thing that probably deserves a lecture all by itself as well, especially the testing that it's gone through. So in terms of our onboard comm system, the radio is off the shelf. So this is a board called the CMC, which we purchased. It was designed by the Cape Peninsula Institute of Technology in South Africa. It's been on a bunch of satellites already. It was on South Africa's first CubeSat, ZA Cube 1. And that was actually the prototype version of this board that flew on that. Performs really, really well. So it's good to have it as the basis of our communication system. It's a VHF receiver and a UHF transmitter, and it supports 9.6 kilobits per second GMSK or 1.2 kilobits per second AFSK. And it can support AX25 framing, or when you're transmitting, it can actually go into a transparent mode where it doesn't do the framing, and it allows the onboard computer, it basically just transmits exactly what the onboard computer sends it, so it allows the onboard computer to be in charge of the framing. And we take advantage of that to use some of the more space industry standard framings on our downlink, which allows us better forward error correction. So for the antenna, as I said, it's an antenna deployment module, and you can see it here on the bottom picture with its cover removed. The problem with having such a small spacecraft is the antennas can't be as small as the spacecraft. The antennas have to be bigger than the satellite is. So the way you get around that is you have an antenna deployment module. You store the antennas inside the satellite until 45 minutes after it's left the International Space Station. And at that point, you deploy the antenna elements. So they're made up of a tape spring, and they're just coiled up inside. And then when we want to deploy them, the doors pop open and the antennas come out. And this was custom designed and manufactured at UCD. The frequencies that we've been assigned by EIRSAT are the uplink is on 145.82 megahertz and the downlink is on 437.1 megahertz. Uplink is 1.2 kilobit AFSK and downlink is 9.6 kilobit GMSK. So Fergal is going to talk a bit about our ground station and all of the modulations and the framing and everything that is the technical details about the uplink and the downlink.
Yeah, so we're building our ground station here in UCD in the School of Physics. So I'm going to start off with just our antenna, where you get a VHF 2-meter Yagi antenna for our uplink and a UHF 70-centimeter Yagi antenna for our downlink. So to feed the data into for our uplink, we have a transceiver, which is the ICOM 9100. So that gives us an available transmit power between 2 and 100 watts. The data feeding into the transceiver is fed by a TNC, which is the SCS tracker DSP TNC. This is going to operate in KISS mode the whole time because we're using the AX25 protocol, and that requires KISS frames. And then the data is fed from our mission control software into a proxy, which is just for connectivity and for our solution. For our downlink, the UHF antenna is connected to our low noise amplifier. So that's a Mini 70 mass preamplifier, so we can get up to 25 decibels gain. The low noise amplifier feeds into our software defined radio receiver. We still haven't decided what receiver we're using, but for current development, we're using the FunCube Pro Plus. That feeds into our GMSK demodulation software, which feeds into our decoding software, and that is routed back to our mission control software. We also, to maximize our communication windows, we have a rotator. So that is going to be the Yaesu G5500. So on the next slide, you can see it actually in operation. So this is our antenna on top of the School of Physics. So we actually get up to 450 degrees of rotation in the azimuthal plane and up to 180 degrees in the elevation plane. So this will give us communication windows of up to about 7 minutes, I think is the maximum we'll get. So then I'm just going to go into a bit of detail on our uplink. So we send data from our mission control software that hits this ground segment proxy. So the mission control software is going to be hosted somewhere on a remote server, and our ground station is going to be up in the School of Physics. So that's just to connect those two together. And as the data passes through this proxy, our KISS framing is applied. That gets fed into our TNC for AX25 framing and AFSK modulation. So our KISS frame is pretty much an AX25 frame, without the frame check sequence. So the image below there is just our X25 frame. So we have a flag at either end of the frame, and then we have our two addresses, so our destination address. So we're sending our data to EIRSAT-1, and then our source address is going to be Dublin 0. We don't have any digipeaters. The next two fields are control field and protocol field. So that just describes what type of frame it is and if we're using any network protocols. Then comes the actual telecommand we want to send, so that's our data. And the frame check sequence is then calculated on the TNC and appended to the frame. That gets sent to our transceiver, and then that's uplinked to our SAT. So once we've got a successful uplink to get our data down, it actually goes through a few processing stages first. So I'm just going to kind of talk you through these processing stages, so it'll make the ground station solution just make a bit more sense. So when we have our data, that gets packetized to the PUS standards. So that's just developed by ESA to standardize the structure and contents of our telemetry packets. This packet then gets framed. So that gets framed to the CCSDS space data link protocol. So that gives us a fixed length frame for our full mission, which is going to be 892 bytes. The 6 of those bytes are going to be our header, and then we've got 886 data bytes. So the reason why it's going to be 892 bytes, I'll explain in a second. But if we actually don't have enough data to fill our frame, we're going to have these idle packets, which are generated just to fill the 892 bytes, which are going to be a repetition of zeros. So we're using Reed-Solomon frames or encodings. So this allows us to correct for errors in transmission. So if the error occurs at the transmitter during propagation or receiver, when we recover the data on the ground, we can actually correct for these errors. So we're using a 255 and 223 Reed-Solomon scheme. So that means we have 223 bytes of data, and we can generate 32 bytes code word. So that means we can correct for 32 bytes, 32 errors in our code block. So the reason why we have the 892 byte frame length is because we're using an interleaving depth of 4. So that means we stack 4 223 bytes packets. So if you multiply 223 by 4, we get the 892, and then we have 4 32 byte code words, which gives us a total frame length of 1020 bytes. So once we have our Reed-Solomon encoded frames, this gets passed through a CCSDS scrambler. So the reason why we scramble our data is that at the receiver, if you have a stream of a repeating symbol, you can lose synchronization. So that can happen in the cases of when we have idle packets involved. So we scramble our data using this polynomial, the x to the 8 plus x to the 7 plus x to the 5, x to the 3 plus 1. So that doesn't matter if you have a full frame of zeros, it'll be randomized, and that can be de-randomized, then de-scrambled on the ground. Once we have our scrambled frame, we prepend our attached sync marker. So that's allows us to locate the beginning of our frame on the ground. And our ASM is going to be 1A CF FC 1D. So the image at the top there is where we're currently at in our data processing stage. So we have our ASM, we have our 4 223 bytes blocks, we have our 4 32 byte Reed-Solomon codes, and then they're all scrambled apart from the ASM. Next, in certain cases during the mission, we're going to use convolutional encoding. So this just adds another layer of forward error correcting. So we're only going to be using this at the very beginning of our mission, and also when we're in safe mode. The reason why we're not going to be using it the whole time is because it actually halves our data rate. So when we're in nominal mode, we just want to get as much data down as possible. So we only use the Reed-Solomon codes. But what a convolutional encoder does, it takes your input bit and you actually get 2 output bits for each one that's entered. So you have a memory buffer of 7 and you use 2 polynomials to encode your data. So we're using 109 and 79, the same ones that were used for the Voyager missions. So you pass each bit through the 2 polynomials, and the resultant of those polynomials are both, generates your convolutionally encoded bit stream, and that's what gets transmitted. Finally, once we have our convolutionally encoded ASM and frame, these are GMSK modulated, and the GMSK signal then is sent over UHF down to the ground. So what we want to do on the ground is do that whole process, but in reverse. So we're going to use GNU Radio, which is this software available for signal processing. We're going to route the data from our SDR receiver into GNU Radio. We're going to use GNU Radio blocks. So GNU Radio allows you to generate flow graphs, and we're going to use standard blocks for the signal processing for the demodulation stage. And we're going to use standard GNU Radio blocks and an open source project, GR satellites, for the decoding stage of our data. So this is the overview of our downlink. This is the full flow graph. So I'm actually going to take you through this line by line, and you're going to see it's going to be the exact inverse of what happened when we're sending the data on board. So the first line is starts with the FunCube dongle. So the main parameter here is the frequency, which is 437.1 megahertz, which is our downlink frequency. This then gets fed into a power squelch. So this just is a threshold. So anything below that threshold will not get passed through. So we've currently set that to minus 100 decibels. So that's a good way to get rid of low power noise that's just lingering in the background. We feed this data, or we feed this into a frequency translating finite impulse response filter. So this just acts as a low pass filter to remove any high frequency noises. So our current threshold is 6 kilohertz. So anything above 6 kilohertz won't get passed through. The transition width is 1.25 kilohertz. So that just defines how steep the filter is going to be. So it actually starts filtering at 4.75 kilohertz. The center frequency here is if there's an offset frequency introduced between your transmitter and receiver, you can correct for this at this point. So it's currently set to 750 hertz, and the sample rate is set to 192 kilohertz because that's the sampling rate of the FunCube. The next block, we actually downsample our data because our baud rate is 9,600 bits per second. If we're sampling at 192 kilohertz, we've got 20 samples per symbol, which is quite a lot. So it's better to downsample here. So we're downsampling to 96 kilohertz, which gives us 10 samples per symbol. Our downsampled signal then gets fed into the quadrature demodulation block, which is where the demodulation stage occurs. So a gain here is introduced, and that's calculated by 2 times our sample rate divided by pi times our baud rate. So the input is multiplied by that constant to give a larger output. Then the virtual sync just kind of tidies up our flowchart to allow data to pass through without having lines crossing through. So then the next stage is stage 2. So then this passes through a decimating finite impulse response filter. So that just creates a Gaussian filter that shapes our signal. So it's a Gaussian profile. The next block is a clock recovery. So this is actually where our synchronization occurs. So the time, our system here is synchronized to the timing of our transmitter. So the omega value there is an estimate of the number of samples per symbol. So because we've downsampled to 96 kilohertz and our baud rate is 9,600, we have a value of 10. So if we didn't, this is the point where we'd lose synchronization. If we hadn't scrambled our data on board and we had a continuous stream of zeros, we'd lose synchronization at this point. And the output here, the data rate should be actually equal to our baud rate. So it actually outputs just one sample per symbol. So it finds the center point of our symbol and it determines whether that's going to be a 1 or a 0. So outputs soft bits. So anything positive is going to be interpreted as a 1, and anything negative then is going to be interpreted as a 0. We have a multiply constant. This was due to there's an inversion happening somewhere. So I think it occurs at the fun cube, but we're not too sure. So just multiply our values by -1, which just inverts everything. So all our zeros become 1s and 1s become 0s. Next, we have our FEC extended decoder. So this actually performs our Viterbi decoding. So it's the convolutional decoding. It's defined the same way as the encoder on board. So it's using the same polynomials, 109 and 79. Here our data rate's halved because every 2 bits you put in, you get 1 out. And again, our memory buffer is 7, the same as what was used on board. We have 2 running in parallel, one at a 1-bit delay, because as the data actually goes in, you don't know which polynomial is going to be synchronized to. So by having 2 running parallel, you are guaranteed that it's going to be synchronized to either one of the polynomials. There's going to be a 3rd stream here, which goes into the binary slicer. This is because at certain stages, again, as I mentioned, we're not going to be using convolutional encoding. So this just bypasses that, and it feeds straight into our sync and create pack PDU, which is where we locate our ASM, which is 1A CF FC 1D. Once we found our ASM in the random bit stream, we pack these bits into bytes, and then we pack our bytes into frames. So our frames are going to be 1020 bytes. So that's our 892 bytes plus our Reed-Solomon code blocks. The final stage of the downlink is just pure decoding. So we feed our data then into a Reed-Solomon decoder. Again, it's going to be where we can have 255 bytes and 223. Here we can define how many code words we have. So it's going to be 4 because we're using an interleaving depth of 4. And it's dual basis, which is just a certain type of Reed-Solomon encoding. That gets fed into our descrambler. So this is where we descramble our data using the same polynomial that was used on board. And finally, the descrambled frame, this is going to be 892 bytes long, gets fed into a network framing block. This was, I wrote this myself just because our mission control software requires certain network framing to be accepted. And then once we've sent our data to the mission control software, that's where the frames get validated and we recover our packets. So now I'm just going to hand you back to Dave, who's going to talk about trying to reach out to the amateur radio community.
Yeah, I might try reload this slide so I get all of it. No, okay. There's some stuff on this slide that's missing for some reason. So yeah.
Do you want me to see if I can share my screen?
Yeah.
Can you see that?
Okay. Yeah. That's good. So one way that you could listen into EIRSAT-1, and you can kind of contribute it as much as you want through this method, is using the SatNOGs project. So for those of you who haven't heard of it, SatNOGs is an open source global network of satellite ground stations run by the Libre Space Foundation. So you can find a lot of information at satnogs.org. And what they do is they provide open source hardware designs and software for ground stations to join their network. And these ground stations are based around Raspberry Pis, RTL SDRs, so as inexpensive hardware as they possibly can achieve, and using 3D printed antenna rotators. And there's loads of people that contribute lots of designs or their expertise or software to make this system work. And how it works is that your ground station joins the network, and then satellite passes can be automatically scheduled on the network, and it'll take care of everything. So it'll automatically schedule the passes to happen. It will automatically demodulate the data, it will decode the telemetry, and it will upload it all into the SatNOGs DB and their database. So you can find out at db.satnogs.org, you can find out like loads of information about all of the satellites that it supports. And you can get basically all the information that other people have downloaded from those satellites. And then that database is used to build dashboards for different satellites. So you can see the picture here that failed to load for me, but that loaded for Fergal, is a dashboard that was built for the Quetzal-1 CubeSat. So it's really cool that you can go on to their dashboard. You can see all the information about that amateur enthusiasts have downloaded from their satellite as it's orbited the Earth. And if you operate a station, then your contributions will go into the database and end up on the dashboard. And this is an unbelievably important tool for many satellite teams all around the world, because there are SatNOGs ground stations all around the world. And I know for a fact that these guys, Quetzal-1, they rely very highly on SatNOGs to get down a lot of their information, because they're just broadcasting it as it's being generated. They don't have the ability to store a lot of information and downlink it when it passes over their ground station. So it's really an incredible tool for that a lot of amateur satellites rely on. And the nice thing is that anyone can do it, because you don't need a license, because it's receive only. And you can get involved as much or as little as you want. You can just go to the website and get the data and play around with the data and do interesting things that way. Or you can set up a ground station and actually contribute and downlink that data from the satellite and put it up into the database. Another way, and this is getting your hands a little bit more dirty, and I imagine that's what most of you guys are interested in, because you wouldn't be amateur radio enthusiasts if you wanted to do things the easy way, is to use GR satellites. So this is a GNU Radio out of 3 module supporting amateur satellites. There's a link here, grsatellites.readadocs.io. It was developed by Daniel Estevez, and it can be installed on Linux, Mac, or Windows. And it's used extensively as part of the EIRSAT-1 ground segment through the GNU Radio companion blocks. So that's the thing that Fergal showed you. Those flowcharts are made up of blocks that you connect together, and a lot of those blocks come directly from GR satellites. It also has a really easy to use command line interface. The command line interface doesn't support EIRSAT-1 yet, but we are working with Daniel Estevez to add support for EIRSAT-1 to GR satellites. So I would say within a couple of weeks, you should be able to basically just fire up, install GR satellites, open a terminal, and type in, something like we have here, GR satellites space EIRSAT-1. And then, if you want to take in data from a SDR app like GQRX, you would stream that in over UDP. So you would let GQRX do the FM demodulation, stream the audio over UDP into GR satellites. You could also just take audio from a real radio. Now we're at 9.6 kilobits, so you would have to have some audio interface that plugs into your data port to get to 9.6. But certainly you could just take audio from a real radio and patch that into GR satellites, and then it can output the data that comes from EIRSAT-1. So the exact same as Fergal's flowchart did. It's just going to start pumping out data like you see here, and this is real data from EIRSAT-1. And you can display that data. You can save the data. You could pass that into a telemetry decoder app, and you could automatically forward it onto SatNOGs. It actually works with SatNOGs, or hopefully you could forward it to us, to the EIRSAT-1 team. Yeah, it'll bring me on to how to help, and please, we really do want your help. So the scariest part of the mission is the initial acquisition of signal. So this is when it's just been deployed. It's powered up for the first time, hopefully. We don't know that. It's deployed its antennas and it's going to start beaconing. It's going to start sending out information about what's going on board. And this is where CubeSats go to die. Like, this is where it all goes wrong for CubeSats. In like a surprisingly large percentage of cases, this happens and then they're just never heard from ever again, and they're just up there floating around, uncontrollable. So this is going to be the nail-biting part of the mission. So, you know, we've got launch vibrations. Did it even survive launch vibration? It's been turned off for a couple of months. Does it turn back on again? The separation sequence. So basically, when it leaves the larger spacecraft, it's the electrical power system powers up, but then there's a software on board that counts down 45 minutes and then goes through various different sequences of burning resistors to get the antennas out, and that all has to work correctly. We don't know the orbit because it's just come off, you know, a larger spacecraft into a slightly different orbit. So the orbit's not well defined, so we don't know exactly where to point the antennas. And this deployment could happen at any place or time. We don't have any control over that. So it could be up to 18 hours before we see it in Dublin, and it's operating totally in the blind for that time. So really the main thing that you can do to help is just to get the word out, and that on launch day, you know, this is our frequency. Please listen out for EIRSAT-1 on launch day, and hopefully someone somewhere around the world will hear it before we do, and just give us some peace of mind that the thing is alive and beaconing and doing its thing before we can start talking to it and commanding it. And, you know, we'll take any sort of report by any contact method. So it could be a fully decoded data, it could be raw IQ, it could be FM audio, screenshot, even just tell us that you heard it or you heard something, and that will be some relief to us. So submit it by our telemetry forwarder that we will hopefully have for GEO satellites, SatNOGs, email it to us, get in contact through the website or Twitter or Instagram. Just any way you can get in contact with us to let us know that you've heard it would be incredible. And another way that we would really, really like to begin you know, working with the amateur community is to help expand our ground segment. So in the next couple of weeks, Fergal and I are going to write a blog post showing how you can set up your satellites to decode EIRSAT-1 transmissions. We will provide recordings that we've made in the lab of EIRSAT-1, so you can try it out. So no hardware needed yet. You can just play back these recordings on GEO satellites and see how it all works, and demodulate the data. Our mission control software is going to be written to accept forwarded telemetry in real time. So what this means is if you're running GEO satellites and you've got a telemetry forwarder, the mission control operators can actually work with the data in real time that you capture in case that we can't use our own data. So, you know, if we've got transient interference or if our receiver is offline, you could route your data into our mission control software and we could continue to operate the spacecraft that way. We also want to experiment with telecommanding the satellite through alternative ground stations. So, you know, there are lots of good reasons to do this. It could be a backup ground station in the Dublin area. It could be somewhere else geographically, far away from Dublin, and that expands our coverage so we can downlink more data. Now, the catch with this is that obviously you need an amateur license and you need the equipment to transmit AX25 frames on VHF, but I'm guessing that's not going to be an issue for a lot of people here. So we'd really love to explore this this concept and bring people into our operations. Early next year, we are going to be taking EIRSAT-1 for a stroll up to Ticknock to do some end-to-end testing. So if anyone in Dublin wants to, you know, point their antennas towards Ticknock and see what they can hear from EIRSAT-1, we'd be absolutely delighted to learn that you were able to hear it and what sort of range you got and what the signal looked like. And so we'll let you know when that's going to happen. So yeah, I think that's it. would be absolutely delighted to take any questions that you have. And here's just a video that Fergal made showing a recording in GQRX being pumped into GR satellites through Fergal's flowcharts, and yeah, showing the data getting demodulated and displayed. Unfortunately, it's a lot of zeros in these frames. I think these were responses to commands. So you just get an ACK back, and it's a lot of padding, but when it's actually in orbit, it'll be downloading a lot of data. So these frames will be absolutely full. So yeah, thanks for your time, and would love to take any questions.
Yeah, thank you.
Thanks very much, David and Fergal, for a very comprehensive presentation. I have to say that the technical detail and what you're asking the amateur radio to do with regards to help has been very well explained there. And I can see by the attendees, there's a lot of, let's say, senior people in the Irish Radio Transmitter Society here tonight as well. And we definitely will get the word out. So what I'll do now is I will go to Derek, because I know Derek's been monitoring the chat, and I think there's already a few questions lined up. Derek, do you want to take it from there as regards to questions?
Sure, okay. Thanks, guys. That was really good, nice and informative. We have a question from Jan. He's two questions, so we can unmute Jan. We can get him in to ask his questions. There he is. Jan, can you hear us?
I guess that worked.
Fire ahead.
Thanks for having me. Great presentation, very comprehensive, absolutely.
Thank you.
But what I missed in your flow graph, Fergal, where's the Doppler correction taking place?
Yeah, so we actually have software that's going to calculate Doppler corrections, because we know how fast the satellite's going to be traveling. So we're going to be feeding that actually into the ICOM, and we can also correct with the SDR receiver as well. So
I think for the downlink, we'll probably do it at the translating FIR filter stage, right?
Yeah, with that frequency offset.
Yeah.
Okay. So that's especially for the FunCube dongle, because that's acting a bit different than most SDR receivers. That's an audio device with a separate channel. I guess that's what you mean by using it.
Yeah, so for now, because we're using the FunCube for testing, we still haven't decided what SDR we're going to be using, but the GNU Radio blocks you can import a load of different types of SDRs into GNU Radio, so we still haven't actually figured out what way we're going to be doing it yet, but I think it's going to be happening at the FIR filter stage.
Yeah. Then only one remark regarding the support of amateur radios. I guess there are a lot of people who want to help. I will be one of them. But one of the main things that we always are looking for is preliminary TLE. So if you can make those available, then I'm absolutely sure that a lot of people will listen.
Yeah, that would be fantastic. Yeah, we will definitely be making the TLEs available.
Okay,
as soon as we have any sort of sense of the orbit, we will be getting the word out.
Okay. Thanks and good luck. Fingers crossed.
Thank you.
Thanks, Jan. Thanks for that. We have a question from Les. I'll just unmute Les now.
Yeah.
Okay, Les, there you go.
Hi, how's it going, guys? Dave, Fergal, congratulations on, from a fellow engineer. Loved your talk, very, very interesting indeed. Have been a big space fan myself for many years, been back and forth to SpaceX and the Jet Propulsion Laboratory and NASA, done a few things. Just interested there on how you accounted there for the magnetorque interference on the systems on board. The magnetorques there give out quite a high level of interference, electromagnetic interference. And did you have any trouble with interfering with the onboard systems? Go ahead.
No. So the one thing they do interfere with, as you might imagine, is the magnetometers. And the way that that's dealt with is there's a control loop that so the magnetorquers are fed through a PWM signal, and for I think it's 100 milliseconds in every second they're turned off entirely, and that's when the magnetometers are sampled. So we know that the magnetometer samples are happening when there's no magnetorquers active. But for the rest of the systems, it's not an issue.
Okay, it doesn't interfere with any of the experiments?
No.
No, or any of the downlinks or uplinks?
No.
No, very well done, guys. Thank you very much.
Thank you.
Thank you, Les. Thanks for that. Okay, guys, if you have any questions, you can stick them in the comments and we'll get to you. We have one here from Don Kelly. We're just going to meet you now, Don. There you go, Don. Off you go.
Guys, great presentation.
Thanks.
Just a question about the beacon, whether it's operating as a CW beacon or is it purely a packets in the X25 packet coming down?
It's packetized.
Okay, that's good. Thanks.
Okay. Thanks for that, Don. We have a question from Dermot. I just got you unmuted now, Dermot.
Yeah, thank you very much for a very interesting and head-scratching operation from an old guy. I just wondered what kind of power the downlink is. What power kind of power are you putting out from the?
In nominal mode, we've actually two options. So we can transmit at 0.5 watts or 2 watts. So in nominal mode, we're going to be transmitting at 0.5 watts. So we've done the link budget and we do have enough power. And then in safety mode, or safe mode, we're going to be transmitting at 2 watts just to make sure we get everything down safe.
Right. Thank you.
And then as well as that, we get a coding gain from the convolutional encoder. So Fergal, you probably know what the coding gain is on that, do you?
I think the convolutional encode gives us another 2 decibels of coding gain.
Okay, yeah. So in safe mode, we'll also use the convolutional encoder. So it gives us the 2 decibels when it's more important that we can hear it than get a lot of data through.
Could I ask again about the software decoding? I mean, taking it down at 9600, do you have are you aware of sound card demodulators? Like many years ago, they had the hardware ones, but I wonder, has it moved on to software demodulators?
Yeah, I believe so. So the method that we've used is the software-defined radio that Fergal's worked extensively on. But we want to look at a hardware modem, which we have looked into. And then as well as that, our ICOM radio has a built-in audio interface, a USB audio interface. So it's when you plug it into the USB in your computer, it's like your computer has an extra sound card that's permanently wired into the ICOM. So that should be possible to get it out of the ICOM that way, as well as using the software-defined radio board.
Lovely. Thank you very much.
Okay, thanks, Dermot. Moving on to Albert. Just going to unmute you now, Albert.
The unmute button.
There you go.
Yeah, great. Yeah, thanks very much, guys, for that presentation, and yeah, particularly thanks for the walkthrough of the GNU Radio flow graph. I've seen a couple of projects that are just kind of stuck that on the screen, and you're left trying to work through those blocks yourselves, which it's tedious when we don't know what you're doing. I was just wondering, and I think you may have mentioned this, about whether a telemetry decoder could be provided. I mean, obviously, for the amateurs are interested in it, but to get beyond the amateur radio community to the makers, people just messing around, to be able to say, oh well, this is the temperature on some panel rather than just a page of hex is great. So if something like that can be made.
Yeah. No, I should have mentioned that's something that we do plan to have, and we'll start publishing it, fairly soon. The reason we haven't up until now is we're constantly going, oh God, it'd be really nice if we had this parameter in there, or oh, we forgot to put in this. So it's probably going to be in flux for a little while longer, and we feel like if we start publishing it, people are going to be using out-of-date ones and that kind of stuff. So we want to wait a little bit more until it's really well defined. Yeah, but definitely, yeah, I think it's the responsible thing to do is to publish all this stuff so that people know exactly what it means.
Yeah, that was going to be my other question of whether, you know, you can make that flow graph available, and, you know, some of the things to play with. But as you say, obviously when it's got a certain level of stability, so that we're not all you know, using out of date stuff, is just it just gets more confusing.
Yeah, so the flow graph, we're pretty happy with you know, how the flow graph works, and as I said, we're working with Daniel Estevez to get the support, so you can just type in like your satellites, EIRSAT-1, and that will take care of all the stuff that's in the flow chart. But sort of what comes after, about what bit in that string of hex means what.
Yeah.
That's the important thing that we need to define, and then we need to make some really nice GUI app or something that people can see in real time with the stuff that they've gotten through their antenna. You know, this solar panel has this temperature and that kind of stuff. And I think that'll be really great for people to see.
Yeah. And are you at all thinking about maybe kind of open source some of that stuff early on that people might be able to help with, or what's your thoughts on that?
Yeah, I think once things are in a stable enough state, I think anything that we can open source and bring in some help would be fantastic.
Cool. Thanks very much.
Great. Thanks, Albert. Thanks for that question. Jim Houlihan, just going to unmute you now, Jim, and you can ask your question. There you go. Are you unmuted, Jim? Maybe come back. Oh, you're there, Jim. Can you?
Okay, can you hear me?
We can hear you now. Yeah, go ahead.
Okay, just thanks for the fantastic lecture and a great description. Just wondering, how long do you expect this mission will last?
That is the big question. So it's really tricky to say, and the reason is, if we come off the International Space Station, so if we're launching into an orbit that's really similar to the International Space Station, that's really low down. So it's like 400 kilometers up, and there's still some atmosphere there, and that can cause drag that degrades your orbit quite quickly. And there's a lot of uncertainty on that. So the short answer is at least 9 months, hopefully up to 1.5 years if we come off the space station. However, ESA have been sort of questioning us lately about whether we could accept a launch on a European launcher into a sun-synchronous orbit. And if we end up in a sun-synchronous orbit, we could easily be looking at 15 years. So somewhere between 9 months and 15 years.
Okay, thanks for that.
Okay, Joe, you're up. 687 GY.
Yeah, okay, yeah, thanks, and that was very interesting. It's my turn next week, guys, and I'm looking at the quality of your presentation. I think mine won't be anything like that. But anyway, no, my question was a simple one. What's the time? I mean, when is the launch expected? And apologies if you mentioned it, I may have missed that.
No, we didn't say it, and we're purposely being a little bit vague, if I'm honest. ESA really don't like us talking about launch dates. The reason being that they haven't manifested the launch yet. So what we're allowed to say is when we plan to deliver the satellite to ESA for the launch, but it could be sitting on the ground for a long time. I mean, a couple of months before it gets launched. If it goes to the space station, it could be sitting on the space station for a few weeks before they bother sticking it out the airlock. So the best we can say is that we're hoping to deliver it to ESA around about this time next year. And from there, hopefully soon after that, it'll get its launch.
Okay, so it's still a bit vague. Actually, as I still have the mic, if you don't mind, Terry, we were talking about power earlier, I think, in answer to one of the questions. I mean, if you're in a low Earth orbit or a synchronous orbit, I'd imagine would the power calculations be quite different, will they?
Yeah, so it depends on what synchronous orbit you're in. So synchronous orbits are usually defined by the local time of the ascending node. So that's the time that it passes through the equator, what the local time directly underneath the satellite is. So, you know, you could be, a typical one could be a noon orbit where you always pass the equator at noon local time. And in that case, you go around the Earth with half the time or a little bit less than half the time you're in darkness, and a little bit more you're in sunlight. And that's kind of similar when you do all the ISS calculations and you average it over a year. that works out fairly similar to an ISS orbit. But if you go into what's called a dawn orbit on a sun synchronous, you're in sunlight all the time, and then you have way more power available to you. But the catch is the satellite gets a lot hotter because it's always baking in the sun.
Okay, thanks.
So you'll have loads of power, but you'll have loads of heat as well. Les has a question. Go ahead.
How's it going, Dave and Fergal again? Listen, you were saying about connecting SDR there to a radio. There is an SDR connection there, an antenna switch called an MFJ1708B SDR and system where you can connect a ham radio, which could be an ICOM IC7300 or a Yaesu FT991A. And you can use that for direct receive from straight down for an SDR. There's a slight modification that you have to make for it, but it's something you might be able to use. It's something that you can buy off the shelf, and it's fairly cheap at about €129 for it. There are the modifications online. You'll see it there on any of the ham radio blogs there, the modification for it, and it's a great there to take a direct link out from the radio instead of having to actually go straight into the bones of the radio. You can take that direct link out from the radio using that antenna unit switch, and as well as that, any other of us radio experimenters, we can use that as well if you want to have an SDR system running straight out from your radio on receive. And you can use a PAN adapter as well. It works as a PAN adapter as well as an SDR receive. So that's something that's off the shelf, and it's not a big expense. So I can send you on the details of it there. There's no problem at any time.
Yeah, that's one of the things we were starting to think about. How do we get both the radio and the SDR?
I can share that. Just share that screen with you there. Oh, it's disabled. No. Is it possible, Adrian, to just share a screen a second with the guys? I don't know whether you can hear me.
You're muted, Adrian.
Oh, yeah. I'll make a co-host now, Les.
Okay, thanks for a second.
Yep.
Okay. Let me see now. Can you see that?
Yeah, I can actually. Yeah, since you dropped it in the chat, I googled it and I found the exact same page myself.
Yeah. So that's it there. A slight modification to it inside. It only needs to put one wire, a bridging wire across there, and it'll work. It'll work for you, no problem.
Great.
Okay, I'll just stop sharing again. No, back again.
Right, thanks for that, Les. We've one other question from Albert.
Yeah, me again. Yeah, no, first of all, thanks, Les, for that. I hadn't seen that MFJ thing before. That looks interesting. No, I just want to jump in an astronomy question if I can. Well, sort of, about the gamma ray module. And I mean, it's tiny for a gamma ray observatory of any sort. I mean, I think the smallest one up there at the moment is probably over a ton. So I was just wondering what the sort of performance and sensitivity of it would be, and how it would compare to other observatories, and is it primarily to be used just for gamma ray burst work, or what's the kind of plan?
Yeah, so well, it's primarily a sort of a tech demo. It's got a lot of stuff in it that hasn't really flown before, and if it works well here, it's going to find its way into bigger satellites in the future. So sensitivity of a gamma ray instrument is usually measured in square centimeters. So that's, the sensitivity, if the area that it would have if it was 100% efficient and caught every gamma ray that passed through it. So because this is inside a satellite, it's got shielding from different components in different directions. So the most sensitive you get is sort of in through, not quite the top, almost in at an angle, and it's about 12 square centimeters. And coming up through the spacecraft stack, it's, it's not that good. Depending on the energy of the gamma rays, higher energy gamma rays will get through it. You don't even see the satellite making an effect there. So when you sort of average over all directions, it's about 8 centimeters squared, which is not huge, but the you know, it's what you can do with it. So straight up, because it's a single crystal detector, you're not doing imaging, you're not doing polarization, so you're making light curves and you're making a spectra. And it's reasonably good at making spectra. It's got quite good resolution for making spectra. And then in terms of sensitivity, really the only thing you're going to be able to see is gamma ray bursts. And
that's what's going to be strong enough, really.
That's what's going to be strong enough. And then you want to know is like, okay, how many of the gamma ray bursts are you going to see? Because they're not all going to be strong enough. So we calculate that at a factor of like 10 sigma, where you're absolutely sure this is definitely a gamma ray burst I've detected and it's not just statistical noise. At 10 sigma, we're going to see about 20 gamma ray bursts a year, which is pretty decent.
That's decent.
It's not bad. It's enough data to keep us busy.
Yeah, certainly it'll do the proof of concept anyway for you.
Yeah.
Cool. All right, thanks, David.
Thanks, Albert. Just on that, we have Les, who's just got a gamma ray question as well. Go for it, Ron.
Okay, Dave and Fergal, I'm just wondering, is the gamma ray burst unit, is it cooled?
It's not.
And if it's not cooled, no. You're just using it's going to be just cooled to space cool, as they say, about 5 Kelvin thereabouts.
So it won't even be that cool. It'll stay around room temperature, really. Now we did a big test campaign just before lockdown where we took the gamma ray Gmod, the gamma ray module to Belgium, and we put it in the thermal vacuum chamber, and we we pumped out all the air and we heated it up and we cooled it down, and we did a couple of cycles, and what we found is that the actual sensitive volume of the detector, which is this crystal called cerium bromide, that sensitive volume is so well thermally isolated from the rest of the spacecraft that there's almost no variation in temperature at all. So we don't need it to be that cool, but you do want to control the temperature so that it's stable. That's the most important for this detector, is that it's the temperature.
So
stable.
do you have heaters on board, I guess?
We don't for this.
No.
So we do have battery heaters.
Yeah.
But we don't have any heaters for the crystal. But what we've shown through testing is that it's so well thermally isolated that we probably won't have to worry about that.
Yeah. If you do receive a gamma ray burst, how long will it take you to track the satellite to the line of sight, or do you just pass on the information to one of the areas that track these gamma ray bursts?
So that's an interesting question, because first of all, EIRSAT can't do localization, which is to tell the observers on the ground, oh, that direction, you look at where the gamma ray burst came from. So it can't do that. But even then, our downlink solution is not ideal because you can't do it fast enough. Even when you can figure out where stuff comes from, they fade so fast that the challenge is to get it down as quickly as possible. Now we work with a team in Goddard that are building their own CubeSat. That's a 6U CubeSat called BurstCube, and they are developing the first ever radio that can talk to TDRS in a CubeSat, specifically to overcome this problem, so that they can get their signal on the ground as quickly as possible when they detect a gamma ray burst. So for us, we'll probably be waiting a while before we can get the data down to actually do the analysis. But we have plenty of storage on board, so we can actually store that data for as long as it takes to eventually get the data down.
But you never know, we might have to look at the Irish and be
Hopefully.
first to that, hopefully. By the way, how much memory do you board?
4 gigabytes.
4 gigs. 4 gigs. Thanks, guys. Much obliged.
Thanks, Les. Don't forget, guys, to put your questions in the chat. We have a few more to go here. Jan just makes the comment, make sure the batteries are charged. It wouldn't be the first with a flat. We're keeping a positive side on this, Jan. These Irish factories are very charged. Chico, you have a question?
What kind of power do the solar panels provide, and if there is any backup in case of a possible fault?
So we have 4 solar panels on board. They're mounted around the edge of the big faces of the satellite. 3 of those panels have 5 cells, and the cells give about 1 watt each. So 3 of the panels give 5 watts. And then we have 1 panel that, because we had to make space for our GPS antenna, only has 3 cells, so 3 watts. But the satellite is spinning the entire time. So you you average out the power that you get, and it works out at more than, at certain times the sun is sort of 45 degrees on to 2 panels. So you don't always just have 1 panel at a time, but it averages out that we get about 7 watts when we're in sunlight. And the backup really is that the EPS has separate channels to receive those different panels. And so it has 3 different battery charge regulators on the power supply board. So if one of those panels were to go bad, there's a very, very small chance that it would affect any other panel. So our backup is just having multiple panels essentially.
Okay, thank you.
Question from Les here. He's getting great value for money on the questions. Go for it, Les. That's what we're here for.
Guys, I just want to ask you about the paint squares on the birds. I think it's from Emo. I know the guy involved through engineering, and I believe some of that is gone on the Horizons spacecraft. I think some of it was tested.
It's on Solar Orbiter.
Solar Orbiter, sorry, Orbiter, wrong one, yeah. And of course, that's bringing back fabulous pictures at the moment. Are you testing a new paint system for him? Go ahead.
So it's this. So Solar Orbiter has the Solar Black. I think Solar Orbiter was originally supposed to have the Solar White as well. Now I'm not entirely sure if they got rid of it entirely or if they just massively reduced the amount of Solar White. But I know it was scaled back significantly at least. So I don't think there's any Solar White on Solar Orbiter. But this is going to be the first test of it in low Earth orbit. And in low Earth orbit, you have things like atomic oxygen that can sort of attack these coatings and break them down that Solar Orbiter doesn't have to worry about. And if these are going to be coating, satellites in Earth orbit in the future, it's important to get an idea of how it behaves and over longer time spans, how that coating performs and how it breaks down.
Yeah, because I know with the Voyager spacecraft, they're almost 41 years there now. They had a lot of problems with atomic oxygen. They were going to worry, but of course they have no way of checking it to see how the structure has held up over the many years it's been in space. So it'll be interesting to see now how the atomic oxygen there works on these paints and stuff for future missions. Probably the next one being EIRSAT-2, and hopefully not too far down the road. Thanks again, guys. Much obliged.
Thanks.
Thanks for the questions, Les. Any other questions there, guys? Are we? That's it, I think. David Fergal, thank you very much for that. Hang on, we have one more question. Is there a beacon transmitter as well as a data transmitter? And will the transmitter start as the antennas are deployed? That's from David. Dermot Manson.
So our normal beacon is what is sometimes called a pseudo beacon because it's not generated by the comms board itself. It's generated by the onboard computer. But what we do have is a watchdog on the comms board, and if for any reason the onboard computer ever stops generating beacons to send, the comms board can take over in a different beaconing mode with a more simple version of the beacon where they're being generated by the comms board itself. And yes, it will start as the antennas are deployed. So we have to have, we can't deploy anything for 45 minutes after we come off the larger spacecraft. We're not allowed to do anything until 45 minutes. But as soon as the antennas are out, we can start transmitting, and we will do so.
Okay, thanks. Sorry for talking in your way, Dermot, there. It's just that you were muted. And Chico's gone to bed. Good night, Chico. Okay, any more questions, guys? We don't have any more in the chat, Dermot or Adrian. Will I have you?
Thanks a lot, Derek.
Thank you.
Well, that was a very worthwhile talk, presentation and Q&A session, I have to say. And as you know, David and Fergal were recording this presentation, so any amateurs or radio hobbyists that are interested can catch up with all the detail that you've provided. So hopefully we'll catch a few more interested people there, because there's a ton of information in that presentation that can be used. It was phenomenally well presented, so thanks very much.
Thank you.
And I think from all of us here in South Dublin Radio Club, and I suppose the amateur radio community worldwide and in Ireland, we wish you the very best of luck.
Thank you very much.
Yeah.
And thanks for having us.
Okay. Yeah, absolutely.
All right. And just before I wrap up here and take the brakes off the mics, it's just to remind you that Joe, EI7 Golf Yankee, will have his presentation next week on radio experiments by Colonel Dennis, EI2B, which is the bookend of the two guys' presentation, because he's considered the world's first radio amateur. So from humble beginnings to orbital spacecraft. Thanks very much.